Chapter 1, Section 1.5, Analyzing Graphs of Functions. Here are our section objectives. Graph of a function. We will be looking at graphs. They are a collection of ordered pairs, and there's an example. The vertical line test, as I mentioned before, it works because if you do any vertical line anywhere, it should only go through one point. That means that that x value is defined at only one value. If you have a vertical line that hits 2 points, one x value is defined at, two y values, so it wouldn't be a function. Domain and range, I'm going to ask you to find domain and range of equations and then also given a graph. So we'll look at this graph and answer these three questions. First, the domain. The domain is where the x is defined for the graph. So here it looks like it starts, the lowest that it starts, or the furthest left is -1. The furthest right is 5. Everywhere in between there, if you go anywhere on the x-axis, you will be able to find the graph. Either above or below, you'll find the graph. So how I'm going to write that is the domain is from -1 to 5. I used a closed bracket for the open circle there at -1, and I used an open, or a parenthesis, a rounded bracket at 5 because it's an open circle. Next two questions are just function questions. So at x equals -1, the y value, or the height of the dot or the point, is 1. F of 2, if you go to 2, find the point, and the y value is -3. Range, you go from the lowest that the graph goes up to the highest that it goes, and where it's defined on the y-axis. So the lowest would be -3. The highest would be 3. And those are both closed circle or solid lines, and so both square brackets. Here's the solution typed out. Zeros of a function. When I ask you for a zero of a function, I'm asking you to take the function, set it equal to 0, and solve. What that will give you is x-intercepts, and so that's what we're looking for when I ask you for a 0. So I've got 3 examples. We'll work through each of them, finding the zeros. So we first set the function equal to 0. This is a, and if it's quadratic, typically we solve this by factoring if it's factorable. If not, sometimes we can solve algebraically. Other times we might have to solve using the quadratic formula. This one is solvable, or it's factorable. So I will factor it, and then I set each factor equal to 0 and solve. So it looks like my zeros are going to be 5/3 and -2. So 5/3, 0, and -2, 0. My 2 zeros for part A. Next one, I set it equal to 0, and here it's not quadratic, so I'm not going to factor. I'll just solve algebraically by undoing everything. So first, square root and squared are inverses. They cancel each other out. 0 squared is 0. I'll add x squared to both sides, and then square root. So my 2 answers are plus and minus square root of 10. So when I write those zeros, here's what they look like. And the nice thing with the typed up solution, they also have a graph, so you can see what those points look like. Last one, I set my equation equal to 0 and solve. When I have a fraction, the first thing I'm going to want to do is multiply both sides by the denominator. That cancels out on the left, and 0 times anything is 0, so it turns the right into 0. Then I'll solve. Add 3 to both sides, divide by 2. So this one has 3 halves, 0 as my 0. All right, increasing, decreasing functions. I'm going to ask you to be able to describe where a function is increasing, decreasing, or constant. I'm going to start by looking at these 3 graphs and answering that question for each. So we'll do increasing. and we'll do it for all three. When you look at where it's increasing, when you look at a graph, you look at it in the direction that you read from left to right. So increasing, increasing. On the first one, you can see the two pink highlighted zones. There's one increasing in the middle one, and then I would say two increasing zones on the last one. When I describe increasing interval on a function, I'm going to use interval notation. Here it's negative infinity to negative 1 and 1 to infinity. I use all brackets here because even though it's a closed dot here at negative 1, 2, you can't contain negative 1 in your increasing interval. It's the maximum of the function. It's not increasing. It's only increasing up until negative 1. Also, when you describe function behavior, you're always going to look at the x-axis when you're describing, not the y-axis. Here I would say negative infinity to 0. So that's where 0 is. And then here I would say negative infinity to 0 and 0 to infinity. As I look for decreasing, I have 1 here in the middle that's going down, decreasing. I got 1 here, decreasing, and none there. So decreasing, I would say negative 1 to 1 here, negative 1 to 1. That's my decreasing zone. Here I would say 2 to infinity, and here none. Last one is constant, and only the middle is constant. That's going to look like a horizontal line. It's constantly at y equals 1. So kind of ran out of room, but constant. Again, it's the x numbers, so 0 to 2. No constant on part A or C. Relative minimum and relative maximum values. When you're looking for a relative min or max, it means that it's the min or max in that little neighborhood, that little area. It might not be the min or max of the whole function, but it is of that little spot. So like here it says use a graphing utility to approximate. So this would be the minimum. It's the lowest point in that area. So it looks like negative 1, 2, 3, a little bit more than negative 3, or a little bit more negative. That's the lowest. So I would say, the minimum is the lowest that it goes. So we use a y value. And I'm going to say negative 3.2. They said negative 3.3. So we were just eyeballing it. If you had a graphing utility, you could get that point using a graphing calculator or using Desmos.com. Average rate of change. Average rate of change is going to be another way to say slope. It is, if you have this curvy line and you want to draw a straight line in between 2 points on the line, it's called a secant line, and average rate of change is going to be the slope of that straight line. So average rate of change, here is basically a slope formula in function notation. So average rate of change might look a little different than slope, but it is just function notation for slope. And so here's 2 examples. We'll do the first one. Let's see if I don't have enough information here. I might just work right here. So find the average rates of change of this function. So this is the curvy line. And the first one I'm going to do is negative 2 to negative 1. So negative 2 to negative 1, I'm estimating this slope right here. So it looks steep and positive, so that's what we're looking for. I need y values to these x values. So like negative 2 comma what? And negative 1 comma what? If I'm going to do a slope, I need full ordered pairs, and the question only gave me the x of the ordered pair, the x-coordinate. So if I look at the graph, they gave it to me. If I didn't have a graph, I didn't have a picture, I could take negative 2, plug it in for x into the function, and out would pop the y value. I do have them here, negative 2 and 2. So when I do average rate of change, I'm doing slope. 2 minus negative 2, negative 1 minus negative 2. That would be 4 over 1, or 4. And I was guessing, steep and positive, and I got 4, so I'm happy with that. Next up, I'll do this one, and it is negative and also pretty steep. So I am going from 0 to 1. So again, 0 comma something, got to figure that out. 1 comma something, got to figure that out. I could plug them into the equation, or I could look at the graph and I can get these ordered pairs, and then I'll do the slope for b. Negative 2 minus 0, 1 minus 0, so it'd be negative 2. 4, negative 2. Even in odd functions, one way to think about it is with symmetry. It is just a way to describe a function is even if it has y-axis symmetry. It is odd if it has origin symmetry. Even, with y-axis symmetry, here is the definition. If you have x and you switch it to negative x, if they're both on the equation or if they're equal, it has that y-axis symmetry. And then here is the odd symmetry, or the respect to origin symmetry definition. So, first equation or first example, it says that this function is odd because of this. And so what we do is we take this function and we plug in negative x for x, and then we see what happens. So if you do this and then you simplify, if you factor out a negative, it goes back to the original. So that means negative, the function, is the same as the function plugging in negative x. That is the definition of odd, or origin symmetry, so that means it is odd. Here is an even one. If you replace x with negative x and it simplifies back to the original, it has y-axis symmetry, which is even. So here I take the original, I plug in negative x for x, simplify, that's back to the original, and that is y-axis symmetry, so that is even. Here is a graphical representation of each. Our first one was odd, and you can see, what I like to do is look in quadrant 1, look here at this, and if you flip it over here and then flip it down here, origin symmetry is both flips. So you can see that line has been flipped over the y, flipped over the x, that's origin symmetry. Also this piece, if you flip it up and then flip it over, you have that piece with symmetry, origin symmetry as well. Here, it's just a y-axis symmetry. There's a line of symmetry right along the y-axis.